Hello students, welcome to this section of 1.5 where we're going to be doing our second part of this section. In this video, we're going to be doing some practice problems using the definition of continuity that we learned in our previous video. So let's get right into it. So here we have a graph of the function g of x. And we're going to be looking at several x values, and we're going to be proving or disproving continuity using the definition we just used. So we're going to start our problem with x equal to -8. So the first thing that we're going to do is we're going to use our first part of our continuity definition, which is to show that the function's even defined there. So let's look at g of -8, and let's see what that is equal to. So here's -8, and the function at -8 is going to be +4. So that is equal to +4. Now, in our second part of our definition, we're going to be looking at the limit, and we're going to really define it from both sides. So let's look at the limit of g of x as x approaches -8 from the left. And -8 from the left, it looks like it's approaching -5 over there. Is equal to -5. And then the limit of g of x as x approaches -8 from the right side. That's going to get us also -5. So the limit of g of x as x approaches -8 is going to be -5. Okay, great. So now let's look at our final part of the definition. And that's to look at whether these two, if the function and the limit are equal to each other. So is this true? Well, the limit of g of x as x approaches -8 does not equal g of -8. Because the limit is -5 and the value of g of -8 is 4. So what can we say? So therefore, those three dots are therefore. So therefore, g of x is not continuous at x equal to -8. And we really need to show all of this work that's right here in order to make this proof happen. If you leave out any of these steps, you are actually going to end up losing points if this were a free response question. So let's keep going. Now we're going to look at x equal to -6. Okay. So our first part is just what is the function's value at -6. So I'm following the function, and it looks like it's filled in right there. So g of -6 is going to be equal to -7. So now our second part of the definition are the limits. Well, we can say, all right, so the limit of g of -6, of g of x as x approaches -6 from the left side is equal to, well, it looks like it's approaching -7. And then the limit of g of x as x approaches -6 from the right side is equal to -7. So that means the limit of g of x as x approaches -6 from both sides is equal to -7. So our final part of this definition is to say, okay, are they equal? In this case, they are. So let's write that out. So the limit of g of x as x approaches -6 is equal to g of -6. So therefore, we can say that g of x is continuous at x equal to -6. And now we're going to do this one more time, but now we're going to look at x equal to -4. So right there. So let's look at the value. So our first thing is, what is g of -4? So g of -4 comes out to be -5. So now our second part is to look at the limits from the left-hand side right there, and then from the right-hand side. So the limit of g of x as x approaches -4 from the left side is equal to -5. And then the limit of g of x as x approaches -4 from the right side is equal to -2. So what can we say about the limit from both sides? Well, since those aren't matching up, the limit at that point does not exist. The limit of g of x as x approaches -4 does not exist. Okay, so we now go into our third part of our definition. Does the limit equal the function at that point? In this case, we're going to definitely say no, because one value, it doesn't even exist. The limit doesn't even exist, so we can't even see that they are equivalent. The limit of g of x as x approaches -4 does not equal g of -4. So therefore, we're going to look at this the same way we did that first problem here. So therefore, g of x is not continuous at x equal to -4. There we go. Let's continue to do more practice problems. So now we're going to be looking at this, but not just in the case of graphs, but we're going to take piecewise functions now. Using all three parts of our definition, we're going to see if these two piecewise functions are continuous at, in our first one, x equal to -2, and our second one, x equal to pi. So let's do our first one first. The first part of our definition is, what is the value at -2? So f of -2. So f of -2 is going to be right here. So when it's -2, we can substitute it into this value. So 3 times -2 plus 2, so that's -6 plus 2, which is -4. So now is our second part of our definition. We need to find our left-hand limit, which is going to be here, and then our right-hand limit, which is going to be that function. So let's do it. So the limit of f of x as x approaches -2 from the left is going to equal to -2 square root of -2 plus 6. So -2 plus 6 is 4, square root of 4 is 2. 2 times -2 is -4. And now the same thing with our second function. So the limit of f of x as x approaches -2 from the right. So now I'm going to use that third equation here. So e to the -2 plus cosine of -2 pi. Well, let's see. E to the -2, that's 1 over e squared. -2 pi, so that's at 0, so that's going to be 1. So plus 1. All right. So now let's look at, and we can't simplify that anymore. So now let's look at the limit of f of x as x approaches -2. Well, in this case, it does not exist because the left-hand limit does not equal the right-hand limit in this case. So since the left hand and the right side are not coming out to be the same exact value, -4, and then I got 1 over e squared plus 1, since they're not the same exact value, the limit does not exist. So in part 3 here, we need to say, okay, is f of -2 equal to the limit as x approaches -2? And they're not going to be equal. So the limit of f of x as x approaches -2 does not equal f of -2. So what does that say for us? Well, kind of like last time in our previous graphical problems, we're going to say the exact same thing, is that the function is not continuous at that point. And now we didn't even have to look at a graph in this case. So therefore, f of x is not continuous at x equal to -2. So now we're going to look at this the same way. And the first part of our definition says, what is g of pi? So I'm going to use our second equation because that's where the inequality says we're equal to pi. And so I'm going to write out e to the pi tangent of 3 pi over 4. And what is that going to get us? Well, e to the pi. And so tangent of 3 pi over 4. So that's going to be 1, 2, 3. So that's going to be in our second quadrant. And since it's over 4, it's either going to be positive or -1. And in our second quadrant, tangent is actually -1. So I'm multiplying this e to the pi by -1, and that's just going to make it negative. So I have negative e to the pi. Now in our second part, we are going to look at both limits. So the limit of g of x as x approaches pi from the left side. And now I'm going to use our first equation because that means x value is less than pi. So I have e to the pi times cosine pi. And cosine of pi, so cosine 1/2 rotation around the unit circle is going to get us -1. So I end up again with -e pi. So then we can go and do our limit of g of x as x approaches pi from the right side. And that's going to be our second equation. And we've already shown the work for that. So we don't really need to do all that substitution again. We know it's going to come out to -e pi. So -e to the pi. And then, so what's the limit of g of x as x approaches pi? And then from both directions, they agreed that they would come out to be -e to the pi. Okay, so now we're going into our third part of our definition. And so what's the limit of g of x as x approaches pi? Is that equal to the function at pi? And in this case, it is. They're both equal to -e pi, or -e to the pi. So they are equivalent, so we'll write g of pi here. Since those are equivalent, well, what can we say? We can say, therefore, g of x is continuous at x equals pi. All right, so now we're going to look at this sort of type of question where we actually have enough information to solve for additional variables. So let's get right into it. Here's our function over there on the right. We want to say what two limits must equal in order for f of x to be continuous at x equals to -1. Well, in order to figure this out, we need to say, okay, the limit of f of x as x approaches -1 from the left must equal the limit from the right side. So must equal the limit of f of x as x approaches -1 from the right. Those are the two limits that must be equal in order for f of x to be continuous. So what does that say for us? Like, well, what does that mean? Let's actually write these equations out. So first, let's write out our left-hand equation. So on the left side, I'm going to be getting 2, so 2 equals, and that's the limit from the left side, so that must equal the equation part in the middle. So we'll say m, and since we're approaching -1 from the left side, so from the left side, it was 2, and then on the right side, we're approaching -1, so we're using our second equation, so m times -1 plus k. So let's simplify that a little bit. So 2 must equal to -m plus k. We're going to do a similar thing in part B, but now we're going to be looking at x equal to 3. So what two limits must be equal in order to be continuous at x equal to 3? So the left-hand limit from the left-hand side of 3 must equal to the right-hand limit from the right-hand side of 3. Let's write that out. The limit of f of x as x approaches 3 from the left must equal the limit of f of x as x approaches 3 from the right. Well, what does that say for us? Okay, so let's look at the left-hand side. So the left-hand side of 3 is going to be using our second equation. So m times 3 plus k must equal the right-hand side, which comes out to be -2. Let's simplify this. So we're going to get 3m plus k equal to -2. So we want to now find the values of m and k so that the function is continuous everywhere. Well, we have two functions that include m and k, and we need both of those to come out to be true so that the limits in the entire function come out to be continuous everywhere. So I need -m plus k equal to 2. That's going to be our first part. And then I need 3m plus k equal to -2. And that's going to be our second part over there. So in order to solve for this system of equations, what I'm going to do is I'm going to multiply our first equation times 3. And so I'm going to get -3m plus 3k equal to 6. And then I'm going to just eliminate those two. K plus 3k is 4k, and -2 plus 6 is 4. So if I solve for k, I'm going to divide both sides by 4, and I'm going to get k is equal to 1. Now that I know what k is, I can substitute that back into either one of these two equations here and solve for m now. So in my case, I'm going to use the second equation. So 3m plus k, but k we know is going to be 1 equal to negative 2. So I'll subtract 1 and I'll get 3m equal to negative 3. And then I'll divide both sides by 3. And I'm going to get m equal to negative 1. So let's look at our two answers. M equals negative 1 and right here k equals 1. And what we're able to say now is that if these two values were true in our equation above, the entire function would come out to be equivalent. Let's do another problem just like this, but a little bit more complicated. So here we go, another function very similar to the one that we just did, but notice how we have some squares in here, additional variables, not very straightforward. But we're going to attack this problem the exact same way that we did last time. So what two limits must equal in order for g of x to be continuous at x equal to negative 2? Well, we want the left and right hand side to be equivalent. So the limit of g of x as x approaches negative 2 from the left. So our first equation must equal the limit of g of x as x approaches negative 2 from the right, our second equation. So what does that mean for us? Well, k times negative 2 squared plus m must equal 4 times negative 2 plus 1. So negative 2 squared is 4, so I'm going to get 4k plus m. And I get negative 8 plus 1, so negative 7. Let's do a similar thing in part b. What two limits must be equal for the function to be continuous at 3? And it must be our left-hand side and our right-hand side limit. So our limit of g of x as x approaches 3 from the left, that's going to be our second equation, must equal our limit of g of x as x approaches 3 from the right. Well, what does that give us? So from the left-hand side, we substitute 3 in. So 4 times 3 plus 1 must equal to k times 3 minus m. So getting it from that piecewise defined function up above. Let's simplify this. I get 12 plus 1, that's 13. And I get 3k minus m. All right, so now the same question, we're going to do the same thing that we did before, where we're going to end up using a system of equations to solve here. So let's write out our two equations. I have 4k plus m equals negative 7. And I have 3k minus m equals 13. I don't need to multiply by anything here because the m's already cancel out. So those are going to cancel out. So I end up with 7k equals negative 7 plus 13. 13 minus 7 gets me 6. So if I divide both sides by 7, I get k equal to 6 over 7. All right, so now I'm going to take that value for k and I'm going to substitute that into one of our equations up above. And I don't think it really matters too much, but I'm going to go with our second equation. It just looks maybe a little bit simpler to work with. So 3k, but I already know k is 6/7, so 6 over 7 minus m equals 13. Okay, so let's solve for this here. What I'm going to do is I'm going to 3 times 6, that's 18 over 7 minus m equals 13. And I like to turn my variable to be positive. So I'm going to move that minus m to the right side, and I'm going to subtract 13 from the left side. So 18 over 7 minus 13 equals positive m. And let's see, 13 times 7, that's going to get me 91. So I have 18 over 7 minus 91 over 7 equal to m. And let's see, now that they have the same denominator, 18 minus 91 is going to get me negative 73 over 7. So both of these values, k is equal to 6 over 7 and m is equal to negative 73 over 7. Those are going to be our values that make our function continuous at every value. I know this really was a lot of practice, so thank you for staying in there this entire time. If you do need any help with any of these problems, please contact me directly. I'm Mr. Hernandez, and I'm always here to help.